Okay, so this is our second lesson on the topic of matrix algebra. Today we're going to talk about families of vectors and fundamental spaces of a matrix. So you have the lecture notes to help you on that. And they are quite detailed, I must say. All right, so uh, again, at least for that first part about the families of vector, it's something that we worked on already last year, but we need to remind of these properties, and then we're going to extend all these ideas. Okay, so what are we really talking about when we were with the term family of vector? So it's the common term, but it just stands for you've got a collection of vectors and you have some index, so you know how to address them like v1, v2, etc. Okay, so and that could be a finite collection or an infinite collection, but in our case, we are going to be in Rn spaces. So most of the time, well, all the times, our collection of vectors are going to be finite, and well, probably the good thing to do for you is just to keep in mind the basic examples with R2 and R3, because they really can help you visualize what's happening for higher dimensional spaces, which you can't visualize. But if you understand what's happening in R2 and R3, then that's okay. That's the deal. You will have probably understood the concepts behind. And I would say that will extend to second semester when we will go to more general ideas of vector spaces. If you have understood what's happening in Rn, you probably will have a very good understanding of what's happening in more exotic spaces. Okay, so, all right. The idea when you've got a family of vectors is, so let's say you've got a collection of vectors, so something like this, v1 up to vp in Rn, and what you want to know is those two ideas. Okay, you've got linear independence and spanning. In French, indépendance linéaire, libre, famille libre, or spanning is the word générative, famille générative. All right, so what do we mean by those two terms? The first thing, linear independence, means when you've got your family of vectors, is any vector new information, or can you find some vectors that you could have created as linear combination of others? Right? The idea is that do you have members that are correlated, or do each of them bring new information? That's the idea, right? And that is going to be what we call linear independence or dependence. And the second idea is that what is the vector subspace that we can obtain if you combine all the vectors? Obviously, you remember the definition of a vector space or a vector subspace is that any linear combination of items stays where you are in the subspace. So if you've got a family of vector, you can create an infinite number of linear combinations. The idea is that what is the space that you are describing when you're taking all those linear combinations. Okay, so picture in the plane, if you've got two vectors, you may describe just a line if the two vectors are collinear, a line going through the origin, because you remember that in order to have a well-defined vector space, you need to have the zero that belongs to your space. But if your two vectors are non-collinear, you will be able to describe the whole R2 plane. Okay, so that's the idea. And what space am I generating? Am I spanning? Okay, so spanning is the word you want to look for. Spanning set. Okay, so let's begin with some formal definitions. Linearly independent set. Your family V1 up to VP is said to be linearly independent if none of its members can be expressed as a linear combination of others. And you have this math expression to check. Okay, so what you want to do when you want to show that, so you are given your family V1 up to VP, and you wonder, are they linearly independent? So you just say, well, let's say that I've got lambda 1 V1 plus lambda 2 V2 plus etc. up to lambda P VP is equal to 0. Does that imply, so the question is on this implication, assumption is that your sum is equal to 0, and what you have to prove is that it implies or not that all the lambda i's are equal to 0 for I equal 1 to P, okay? If so, then your family is linearly independent. Otherwise, linearly dependent. Okay, so in French again, libre, non libre. All right, so the question is, why is that a good mathematical description of this idea? None of the members of the family can be expressed as a linear combination of others. What's happening if this is not true? If this is not true, well, the contrapositive of this proposition, one member can be expressed as a linear combination of the others. Okay, so I don't know, let's say that, so you've got your family, V1 up to VP, let's say that for some K, so what does that mean in terms of math? It means that there exists K that is in between 1 and P, such that the vector Vk is expressed as a linear combination of some or all of the others. So alpha I Vi, let's write it this way, I to P. It just means that its Vk is equal to alpha 1 V1 plus alpha 2 V2 plus alpha n Vn, alpha P Vp, sorry, I went up to order P. And some of these alpha coefficients, so maybe just one, but maybe more than one, that are not equal to 0. Of course, otherwise, if they are equal to 0, it just means that the Vk is equal to 0. And if you've got a 0 vector, then all right, that's not interesting. That's it. So if one of your vectors, depends on the others, it just means that you have this linear combination with some coefficients that are non-zero, and it's not linearly independent. But if whatever the combination you are creating like this, okay, whatever combination you are creating, you must get that all the lambda i's have to be equal to 0. It means that none of the vectors can be expressed as a linear combination of the others, and so that you have linear independence. Okay, let's see a few of the consequences or the properties we can get from this definition. So first one, a family containing the 0 vector is linearly independent. Of course, if you've got the 0 vector, you can write that it's just going to be any vector can be written as itself plus any times any number times the 0 vector. So you shouldn't get the 0 vector in your family. Second, a family with a single vector is linearly independent, of course, if it's not the 0 vector. Okay. All right. A family with only 2 vectors is linearly independent if they are not collinear. Of course, that's the only way you can make linear combinations with two vectors. A family with 3 vectors is linearly independent if they are not coplanar. Right, so that's just the definition of if you make a linear combination of 3 vectors, you get if one vector is the result of the linear combination of 2 others, it just means it belongs to the same plane. Okay, so that seems quite obvious. And a family is linearly dependent if at least one of its vectors is a linear combination of the others. So this is things we've already said. So that's it with that first property of linear independence that we were looking for in our family of vector. Let's go now to the second property. What is the subspace that we obtain if we combine them all? So you've got this definition that we've probably already seen. We're going to denote that the span, okay, of the family. So you've got your family V1 up to Vp. The span, denoted span V1 up to Vp, is the set of all the linear combinations that you can make with those vectors. And of course, this is a subspace because that's just the definition of subspace. It's the linear combinations are still inside. Okay, so what are the things that we have? All right. Well, it seems pretty obvious, but it's probably things we need to say. What does it mean that some vector v belongs to the span of your family? That just means that you can express v as a linear combination of those vectors. So that's why we translate that into math. There exist some coefficients, lambda1 up to lambda p, such that v can be expressed as a linear combination. So lambda1 times v1 plus etc. lambda p times vp. Okay, what we get next is that if the family is spanning, but also linearly independent, then this decomposition is unique. What's the difference between this line here and that line here? It stands in the, there exists a unique symbol, okay, with the exclamation mark, right? So there exists a unique, okay, let's prove this, right? So, what do we have? We have, sorry about this, we have V1 up to Vp or spanning the space V. We capital V. Okay, we take some vector V that belongs to V. That, what does that mean? It means that there exists lambda 1 up to lambda p such that our V is equal to lambda 1 V1 plus lambda 2 V2 plus etc. plus lambda p Vp. And what we say is that if, so maybe I should have, well, let's keep the lambdas and we will express the linear independence with some other letter, okay? And we want to show that if the V1 up to Vp are linearly independent, then this decomposition is unique. So as usual, when you want to prove uniqueness, you will assume that you have another one and obtain a contradiction. Assume that there exists also lambda 1 prime up to lambda p prime such that v is equal to lambda 1 prime plus etc. v1 plus lambda p prime vp. Okay, there exists another linear combination of the two of these vectors, right? It has both coefficients lambda I and lambda prime I. Okay, what do we get? We get that, of course, as they are both equal to vector v, this and that are equal to each other. Okay, so what does it imply? It implies that I've got lambda 1 v1 plus lambda 2 v2 plus up to lambda p vp. That should be equal to lambda 1 prime v1 plus lambda 2 prime v2 plus etc. up to lambda p prime vp. Okay, so what does it imply? It implies that let's put everything on one side. I get that lambda 1 minus lambda 1 prime v1 plus lambda 2 minus lambda 2 prime v2 plus lambda p minus lambda p prime vp is equal to 0. Okay, but now let's use our hypothesis of linear independence. Do you see that? Use linear independence. What do we get? Linear independence tells us that maybe we could use some other letters. Let's use alpha. My family is such that if I've got anything like alpha v1 plus alpha 2 v2 plus alpha p vp is equal to 0, then, okay, so the properties in the implication, all right, then if we've got such a linear combination equal to 0, it implies that all the alpha i's are equal to 0 for all I equals 1 to p. So that's exactly what we have here, all right? What we have here is such a linear combination, right? It's exactly the same kind of thing as the one we have here. So what does it imply? It implies that, so what plays the role of the alpha I of the lambda I minus lambda I prime? Okay, so that means that for all I, lambda I minus lambda I prime is equal to 0. So that implies that lambda I is equal to lambda I prime. Okay, so either if you assume that you had two different linear combinations, you get a contradiction. So your assumption is that is wrong, and so you have just one single linear combination. Or if you just went with the flow and assumed that there was another writing, the only possibility that you obtain is that the coefficients are exactly the same, so that the writing is unique. Okay, so this is absolutely fundamental. If you've got a family that is both spanning and linearly independent, then you can describe anything that belongs to the span space with a unique set of coefficients. And these are what we call, well, the coordinates of the vector v in that family. Okay, and this is exactly the definition of a basis. Okay, a basis of a vector subspace is any family that is going to be linearly independent and spanning. You need both to have a basis.